Hi guys, this is Dr. Anna, and we continue with the fourth segment of the geologic time in historical geology. And we finished the relative ages, and now we are on the absolute ages. Let's start with a little bit of history. The first person we have to mention is Henry Becquerel, who lived between 1852 and 1908. And I have a little movie about him, so let's listen to it.
Henri Becquerel is one of those scientists whose talent was rewarded by chance. He was a brilliant physicist from a family of scientists. His father went to Polytechnique, he went to Polytechnique, and his son went to Polytechnique. Like his father, Henri Becquerel was interested in fluorescence. Fluorescence, the capacity that some materials have to emit light under certain conditions. At the time, X-rays had just been discovered. X-rays are invisible, and yet photographic paper reacts with them, just like with a very intense light. Becquerel was interested in this strange behavior of light, and so he started to examine it from his point of view as a fluorescence specialist. He decided to carry out experiments with a highly fluorescent material called uranium. That's right, uranium. Today, we have forgotten that this substance was once used because it glowed. People even used it to give a bit of color to their crockery without the slightest idea that uranium might have other properties. For his experiments, Becquerel took uranium salts, conditioned them so that they became highly fluorescent, and looked to see if the photographic paper reacted as with X-rays. And, lo and behold, it worked. He continued his experiments until one day he left non-fluorescent uranium in total darkness together with photographic paper, which reacted all the same. He realized that the photographic paper was not responding to the fluorescent properties of the uranium, but something else. Radioactivity. There, the secret is out. Not only does uranium emit pretty colors after being exposed to light, it continuously emits an invisible and powerful ray which no one knew anything about. And that's what was making the photographic paper react. The discovery captured the curiosity of young researchers, including a certain Marie Curie, who decided to make it the subject of her PhD thesis. It was such an exciting project that her husband Pierre abandoned his own research on magnetism to work in collaboration with her. They couldn't have imagined the effects of radioactivity. Pierre and Marie Curie managed to isolate radium, an even more active element than uranium. Becquerel took a tiny sample, put it in his pocket, and ended up with a severe burn. Pierre Curie suffered the same misfortune with his arm. On both occasions, the wound took 6 to 8 weeks to heal. For their research, Henri Becquerel and Marie and Pierre Curie received the 1903 Nobel Prize for Physics. Henri Becquerel died 5 years later, aged just 55. In his honor, the Becquerel has been adopted as the unit for measuring the activity of radioactive substances.
Marie Curie's original name was Maria Sklodowska-Curie. She lived between 1867 and 1934. When Henry Becquerel figured out that there is an interesting radiation which comes out of the uranium minerals, she suggested Marie, who was looking for a PhD topic, to work on this and figure out what kind of radiation is coming out from the uranium. So she decided to work on this, and as you could hear it in the movie, her husband also quit his studies of magnetic material and started to work with her. The lab they gave her, actually the lab they gave her was an airplane hangar, so it was pretty bad. So I have a little movie about that.
Marie Curie was a pioneer in the field of radiation research and the first woman to win the Nobel Prize in 2 different categories.
Marie Curie was a towering scientific intellect in a Victorian era when opportunities for women, and opportunities for women academically especially, were extremely few and far between.
Marie Curie was born Maria Sklodowska in Warsaw, Poland on November 7, 1867, to a family of prominent educators.
She had to study underground because she wasn't able to be accepted into the men-only University of Warsaw. She then had to leave the country to get her PhD. She was the first woman to receive a PhD degree from a French university.
She came to Paris for her education and met Pierre Curie.
Marie shared lab space with fellow scientist Pierre Curie. They were married in 1895 and had 2 daughters, Irene and Eve. Marie trained Irene to be her assistant, and in 1935, Irene won a Nobel Prize as well.
Marie Curie and her husband began studying the radiation and the properties of uranium.
Marie and Pierre's main discoveries were the ability to isolate the radioactive elements, which came from the uranium-based ore called pitchblende. They discovered 2 new radioactive elements, radium and polonium, which is named for Marie's country of birth, Poland.
In 1903, Marie and Pierre were awarded the Nobel Prize in Physics, along with Professor Henri Becquerel. Marie was the first woman to win a Nobel Prize.
Curie and her husband were absolutely single-minded in the pursuit of their research. In fact, when they were awarded the Nobel Prize, they refused to go and accept the prize personally because it would interfere with their research.
Pierre Curie died from a horse carriage accident in 1906. Despite this loss, Marie continued their work and was offered her husband's teaching position, becoming the first female professor at the Sorbonne.
Curie's research was key in understanding the effects of radioactivity and in quantifying those effects on living cells. She really established the field of radiation therapy for cancer.
Marie Curie made history again when she was awarded the Nobel Prize in Chemistry in 1911. She was the first woman to win 2 Nobel Prizes.
It was through Curie's research that medical use of X-rays became really a possibility.
During the First World War, Marie Curie herself carried many portable X-ray pieces of equipment to the front lines to help the wounded.
Curie founded the Radium Institute to continue her research. Due to her prolonged exposure to radiation, she contracted leukemia and died in 1934.
Marie Curie is such a role model, especially for a woman in science. The impact of her work, the scientific integrity and the drive that she had is truly an inspiration to all of us today.
This picture shows the pitchblende, the uranium ore she was working with, and this is her notes, which is now in the library on Sorbonne at the university. And if you want to look at it, or just, you cannot take it away, of course, but you can look at it. You have to sign a form which lets you know that it has a lot of radiation if you want to touch it or you want to look at it. So it's really weird. They keep it under glass so the radiation wouldn't come out. It's very interesting. Just to summarize, she was the first to use the term radioactivity. She was the first woman in Europe to receive her doctorate of science. In 1903, she became the first woman to win a Nobel Prize for physics. And of course, this award was jointly given to Marie, her husband, and Henri, they said, Becquerel. And this was for the discovery of radioactivity. 1911, she got the second Nobel Prize, chemistry. In 1911, I believe, she came to America with her daughter, and this was when the feminism was really big in America. They were so happy to see her, and all the women were celebrating her for the Nobel Prizes. They gave her a gram of radium. President actually gave her the radium, and she flew back to Europe, to Sorbonne, with the gram of radium in her pocket on the plane. So people had no idea about the radiation and how bad it could be. It's just such an interesting story. I just want to tell you that I was a young woman scientist, and she was my hero. I read everything I possibly could read about her. So if you're a girl and you like science, it's very important, I think, that you read about her and she becomes your hero as well, because we really need heroes. I think it's very important for us to have somebody to look up on, because her life is just so amazing. It's so important to let her close to you, because then you get the beautiful, the peace, how beautiful science is. It's so important, I truly believe. So this is the hangar where she was working. And this is a picture of her. And now let's talk about the science of the radioactive age measurement. Remember, we know that chemical elements are made up of atoms. In the nucleus of the atoms, there are protons and neutrons. What do we know about the proton? Right, the protons have one positive charge. And then we have neutrons, which are neutral. They don't have charge. If the number of protons are the same, which is equal with the atomic number, but the number of neutrons are changes, we call them isotopes. And I'm going to show you examples right here. These are the well-known isotopes. One is the oxygen 16 and 18, and it shows you the protons is 8, and the neutrons in this case is 8 also. So the atomic mass is this 15999, really the mass number. So atomic mass is the average weight of the different isotopes, but the mass number is in this case is 16. So that's why we call it oxygen 16. And when we look at the oxygen 18, it still has 8 protons because oxygen has 8 protons, but it has now 10 neutrons. See, there is 2 extra neutron right here. So therefore the mass number here is going to be 8 plus 10, which is 18. And the atomic weight is 17.999, which tells us that the oxygen 18 is more frequent than the oxygen 16. So that's the oxygen. And now we're going to look at the carbon. Carbon has 3 isotopes, the 12, 13, and 14. So let me go to the next page, and I think I have an empty page there, and I can draw it for you. So the carbon has 3 well-known isotopes. I'm going to draw here. This here is going to be the atomic number, number of protons, number of neutrons, and the mass number. Okay, so in the first case, carbon has 6 protons. Atomic numbers every single time is going to be 6. And the number of protons are going to be 6 as well, because the atomic number is equal with the number of protons, okay? So atomic number of carbon is 6, number of protons are also 6. In the first case, the number of neutrons as well is 6. So what is the mass number? The mass number is going to be equal with the number of protons plus the number of neutrons. So 6 plus 6 is equal 12. So in this case, the mass number is going to be 12. So we call this the carbon 12 isotope. So the 12 just shows you that it has 6 protons plus 6 neutrons. Because from knowing the number of protons and the mass numbers, you can calculate the number of neutrons. So let's say if I say that here the mass number is going to be 13, I can ask you how many neutron does it have? Then you can calculate that 6 plus what is 13, and you know that that's got to be 7. So 6 plus 7 is 13, so this is going to be the carbon 13 isotope. The last one, if I say that the last one has a mass number of 14, then how many neutron does it have? See, 14 minus 6 is going to be, so it will have 8 neutron, because 6 plus 8 is equal to 14. So this is the carbon 14. Have you guys heard about the carbon 14? Probably you didn't hear too much about the 12 and 13, but definitely heard about the 14. Why? Because we know the carbon 14 is a so-called radioactive element. But first, let's see the 12 and the 13. These 2 carbon isotopes are stable isotopes. What that means that when they were formed as carbon atoms, the 12s were formed as 12s and the 13s were formed as 13, and they are going to be 13 until the end of the world. So if we look at the ratio, the carbon 12, carbon 13 ratio, it's going to be a constant number, which means it's not going to change through time. So it's going to stay like that forever. On the other hand, the carbon 14 is a radioactive isotope, radioactive. When we say that element is radioactive, that just means that their nucleus is not stable. So through time, it will decay through time into another element, which just means that if you look at the ratio, let's say to carbon 12, which is stable, to carbon 14, it's not going to be constant changes. Okay, so that's the This is how I wanted to show you the isotopes. So hopefully you will understand that the number of protons are always the same, because only the atom with 6 protons is what we call carbon. If the proton number would change, then it wouldn't be a carbon atom anymore. And what can change is the number of neutrons. See, because that doesn't change the name of the element, it just changes the mass number. See, it's 12, 13, and 14. And that's how we tell the different isotopes apart, that we put C12, C13, C14. I hope you understand this. So the elements with unstable nucleus, we call them radioactive elements, or parent isotopes, undergo spontaneous change, we call it radioactive decay, until permanent or stable configuration is reached. We call those daughter isotopes. There is 3 types of emission from the nucleus at fixed average rate. This is really important, that the decay rate is fixed and it's characteristic of any particular isotope. So it's different for different elements, but it is very characteristic of any particular isotope. Okay, so every single carbon 14 will decay at the same rate. Every single uranium 235 will decay at the same rate, and so on. So this here is the so-called nuclear symbol. This is the symbol of the lithium. When we're talking about nuclear symbol, it's really, really important that we will show the mass number, because that way we can calculate the number of neutrons. Okay, so lithium atomic number is 3. Its mass number is 7. So therefore, what do you think? How many neutrons does lithium have? Because it has 3 protons. And the 7 is the mass number. So it's very simple to calculate the number of neutrons. 7 minus 3 is equal 4, so it has 4 neutrons. As you can see, upper number is going to be the mass number, and lower number is going to be the atomic number, and then you put the symbol of the element. So that's what we call nuclear symbol. That's a big name, but it's easy to understand. Now, I want you to write down the nuclear symbol for the chlorine isotope with 18 neutrons. So, of course, you have to have a periodic table, because we don't know the atomic numbers without the book. So, we need the chlorine, and what we know that it has 18 neutrons. So we have to look up the atomic number of the chlorine. Hey Siri, what is the atomic number of chlorine? 17. So the chlorine atomic number is 17, and that goes down here. How do we get the mass number? Remember, the mass number is equal to the number of protons plus the number of neutrons. So now we know that the atomic number is 17 and it has 18 neutrons. So how do we get the mass number? Yes, we just add it up. Really simple. So 18 plus 12. So the mass number of this isotope is going to be 30. So we just did that. This is the nuclear symbol for the chlorine isotope with 18 neutrons. So it's 30 and 17, and the element symbol chlorine. So it's simple. Now we're going to talk about the different types of decay. But I think I'm going to stop right here, and I'm going to continue it in the next segment. I'll see you there.